Alright, welcome back again to our course in ENSC106, and right now we'll be discussing a new topic on stresses and strains for members in direct shear. So if you notice that I mentioned the word direct, it's simply because there's still another type of shearing stresses associated with flexural loadings. So right now what we're only going to cover is those members, like for example like bolted connections and some elastomeric pads or something like that, those members that are subjected only to direct shear. Okay, and recall that when we say shear, it's just simply the or it refers to the forces that's acting parallel to the surface area concerned. Okay, so an example of direct shear. So here in our lecture handout, okay, so we have here members in direct shear. So it can be, or we can have single shear. You can have single shear, we can have double shear, or we can have punching shear. So for example, we have these two let's say tension bars right here. So once you try to pull this apart, and this tension bar is being fastened by a rivet. So once you pull this apart, then the rivet will experience a shearing stresses right here. Okay, so this is single shear simply because the shearing plane is only one. Okay, another example is this figure 4-2b, and this is an example of double shear. So sometimes, or some design of connections are like this, like for example a clevis pin connection, but this is a bolt. So this one is a bolt, and we have this one member, and another member is right here. So once you apply a load, okay, because this is a two-part member, then it's actually it's going to shear at 2 points. So right here and then right here. So that's why it is a double shear. Okay, so meaning that you by having a double shear, it means that you have greater area as compared to just having a single shearing plane. Okay, so in that way it makes the connection stronger. Okay, so another one is this punching shear. So this one is basically it is just shearing through this material or workpiece, except that the shearing area is right here. Okay, so it's like a punch. Okay, so I guess it's that's enough for these figures. So now let's go on to the equations. Now for the equation, the shearing stress is just simply the limit of delta VO over A. This is the internal shear force, and this is the area concerned. So as delta A approaches to 0. But the same with what we did with axial stresses, sometimes we only deal with the averages. So therefore it's just simply like this. Okay, and the key in solving these stresses and strains for the direct shear is that you have to determine what is this area. Okay, so if it is double shear or whatever. Okay, now for the shearing strain. For the shearing strain, we have right here, for example, an undeformed element. So once you apply a force, okay, so this element will deform. Let's say something like this. Okay, so original position is it's right here, but then because of the shear force, then it moves to this point. Okay, so that means that we have a deflection right here, right? That's a deflection, and let's say this is our original length, and the angle is what we call the shearing angle. Okay, so that's gamma. Okay, so if we write a mathematical expression, so the tangent of this tangent gamma is equal to this deflection divided by this adjacent side. So that's just delta L. So we can also take the limit as delta L approaches 0. However, if since sometimes or most of the times you are dealing with small angle, then this tangent gamma is approximately equal to the gamma itself. Okay, so just take note of this. This is small angle approximations. Okay, and if this is strain and we already have the stress, then the relationship is simply G times the gamma. Okay, so the shear stress is equal to G. This G is what we call the modulus of rigidity, so something like the E in axial loadings, and then this one is what we call the shear strain. Okay, shear strain in regions. Okay, and then this one is, let's say, megapascals, and this one is also would be in megapascals. Shear stress. Okay, or PSI. Okay, so I guess that's all we have in this direct shear. So now we'll have a sample problem. For the first sample problem that we have, this one is taken from the textbook by Philpott. This is this is problem 1.13. Okay, so it says here, for the clevis connection, for the clevis connection shown, determine the shear stress in the 24 mm diameter bolt for an applied load of P is equal to 175 kilonewtons. Okay, so we have this connection, clevis connection, and we have this member 1 and then another member, let's say member 2. So they are both subjected to a force P, and these two members are connected by a bolt. Okay, so for the solution is first let's draw the free body diagram, and right here this is the section view, and because we have a force P right here and another force P going in this direction. So if we cut a section right here, so let's say we'll only consider this portion, then this will be the free body diagram. Now if I consider only this portion, then this will be the free body diagram. And if we consider this middle portion only, so this will be the free body diagram. Okay, so anyway, whichever free body diagram that we'll use, it's gonna be the same. Okay, so if we consider only this one, for example, if I make a cut right here, okay, so what will be the forces for our free body? it will be the force, this force P right here, and then half of this portion, right? This bottom portion of the clevis. Okay, so if this is P over 2, then at the section, that's gonna be our shear force. Okay, so therefore, right here, we can just write VP, or V is equal to simply P all over 2. Why? Because if you just apply the equilibrium equation, then it's just P minus P over 2, then that's just P all over 2. So what is P? P is 175, right? 175 kilonewtons divided by 2. So this is 87.5. Or I guess we should rather write here the step. Solving now for V and area. Okay, so for the area, we have A. A is just simply pi d squared all over 4, and this is 452 point, I think this is 39. And this is m squared. Okay, so area, that's the area of the section. Okay. So if that's the case, then the stress therefore is, so the stress is shear stress equal to V all over A. So this is just simply 93.42 megapascals. Okay, so if we use free body diagram, letter C, then this will be V, right? But we will also have 2 times the area. Okay, so it's just it will turn out that it will also produce the same value of the shear stress. Okay, so let's write it here. Let's check. Okay, so checking using FBD of C. Okay, so if you take the summation of forces along x equal to 0, so this will be this P is equal to V plus V. V plus V, so this is just 2V. Okay, so V is equal to P all over 2. So this is 175 all over 2, and this is just the same as 87.5 kilonewtons. And for the shear stress, right, V all over okay, so for the shear stress, this is V all over A, and the value of the shear force is just simply P over 2, and that's we have 2 values of P over 2, and so it's just P over 2 plus P over 2 divided by 2 times the area, because we have area right here and another area, so it will again turn out that they have the same value. So here 193.42 megapascals. Okay, so the next problem is taken from textbook by Philpott, but this is problem 1.70. Okay, so it says here that for the connection shown, the average shear stress in the 16 mm diameter bolts must be limited to 210 megapascals. Determine the maximum load P that may be applied to the connections. So this is our connection, and it is composed of two angle bars and subjected to this axial force or this external force P. Now these two angle bars, they are fastened together using 3 bolts, and we have these gusset plates inside in the middle. Okay, so looking here, so if this is our connection, then if we make a section cut, then what we see is something like this. So therefore, what we will have is we have 2 shearing planes per bolt right here. Okay, so the problem says that we are to determine the maximum load P. So what is this value that may be applied to the connection if we have a limited 210 megapascals per bolt? Okay, so for the first step, let's draw the free body diagram. Draw the FBD. Okay, so okay, so if this is our total force P, then there's gonna be a shearing force right here, right? So we have 1/6 of the value of P, then another 1/6, and then another 1/6 right here, and also in these planes. Okay, so let's write this is V all over 6. So this is just one portion, so 1/6 times 6, you get a full value of P. Okay, so let's write here, this is top view. Okay, so now let's write V total is just simply equal to the P total. And for the area total, so we have pi d squared all over 4. That's the area of the bolt, right? That's the area of the bolt. Okay, and how many bolts? So we have or how many area do we have right here? We have 1, 2, 3, 4, 5, 6. So let's just write times 6. And this is 1206.37 mm squared. Okay, so that's the total area. But if we only want the area of the bolt, then this is just simply pi d squared all over 4, or you could just divide this by 6. This is 201.06 mm squared. Okay, so you have the area of the bolt, and you have the limited value limiting value of the stress. This is 200 megapascals. So shear stress is equal to V all over A, and this is what we are going to find. V is equal to shear stress times the area, and the shear stress is 210 megapascals, right, times the area of the bolt, right, this is per bolt, times 201.06 mm squared. So this is 42,223 newtons. I guess we should rather use the total area. So let me redo this. So let's just use this total area. Okay, so for the shear stress, so this will be our total shear all over E, and the shear force, which is just equal to P, is just 210 megapascals, right, times the total area, because this is the interconnection. So I think we should rather use this the full capacity of this bolted connection. So 1,206.37 mm squared, and this is 253.34 kilonewtons. Okay, so again, this is total. This is just V is simply V total. Okay, so I think that's all. And what else? I think in the next video we'll do 2 more problems for these members in the Red Shear. Okay, our third problem is that this one is taken from the same textbook by Philpott, but this is problem 1.19. The problem says a hydraulic punch press is used to punch a slot in a 10 mm thick plate. If the plate shear at stress of 250 megapascals, determine the minimum force P required to punch a slot. Okay, so here is our 10 mm plate, or 10 mm thick plate, and here's our punch. So once this goes down, then there's gonna be a slot that being punched, and the dimension of the slot is 75 mm on center, and this diameter is 20 mm. So we are asked to find it. We are asked to determine the minimum force P required to punch a slot if this plate has a shearing stress of 250 megapascals. Okay, so the area right here is just simply the area. This is the area, right? The area, let's say the perimeter of the slot times the thickness. So first is to solve for the area, and the area is just simply, right, pi d. So this half of this pi d plus half of this pi d, which is which gives you a 1 full circle. So this is just pi d plus 2 times the length. So the length from center to the center. Okay, so what is our diameter? This is 20 mm plus 2 times 75. This is equal to 212.83 mm squared. Okay, so now since we have this area and we have the allowable shearing stress, then we can solve for the force. Solving now for the force. So this is V is equal to the shear stress times the area. So this is 250 megapascals times 212.83 mm squared. And what we get right here is 53.2 kilonewtons. Okay, so usually the problems are straightforward. Okay, so the one last problem that we'll have is this one. Okay, this one is taken from the textbook by Beer et al. And this is example 2.10. The problem says a rectangular block of material with G, this is the modulus of rigidity, which is equal to 90 ksi, is bonded to two horizontal plates. The lower plate is fixed. So right here, we have plates right here. This one is fixed and then this one is moving. And this material has a rigidity of 90 ksi. The lower plate is fixed while the upper plate is subjected to a horizontal force P. Knowing that the upper plate moves through 0.04 inches upper in under the action of the force, determine the average shearing strain in the material, and letter B, determine the force exerted on the upper plate. Okay, so here's the dimension. We have 2.5 inches by 8 inches for the plates, and along the vertical direction is 2 inches. Okay, so for the solution, so let's draw the FBD. Okay, so let's say this is our original position. So because of the upper plate movement, then it's gonna be something like this. Let's say this is upper plate and this is lower plate. Okay, and right here it moved, right, this one, it moved 0.04 inches, and this one is 2 inches, right? Okay, so 0.04, this distance, and then we have a dimension that's given. This is already 2 inches. Okay, so solving for the shearing strain. So this one is just simply approximately to the tangent of 0.04 all over 2, which is 0.02 inch per inch, or radians. Radians. Okay, so this is the average shearing strain, which is just simply the distance, right? The ratio of this opposite to the adjacent. And this is 0.04 divided by 2 inches. So that's our shearing strain. Okay, and now let's solve for the shear stress. Solving now for the shear stress. Okay, so shear stress is equal to simply, since we have the modulus of rigidity, so G times this shearing strain. So this G is equal to 90 ksi, or 90,000 pounds per square inch, okay, times the shearing strain of 0.02 radians, and this is equal to 1,800 pounds per inch squared. Okay, so now we have this average shear stress, then I think we have solved this letter A. And to solve for force P, of course, we need this shearing stress, because once you have the shearing stress and you have the area, but the area is the area that refers to 8 times 2.5, so we can solve for P. Okay, so solving now for force P. Okay, so here's our equation. The shear stress is equal to V all over A. So V is just simply the shear stress times the area. And take note, this V, this is our this is it. This is the P. And the shear stress is 1,800 psi, okay, times the area of 2.5 by 8. Okay, so why is the area 2.5 by 8? Because that's the area parallel to the force P. So this is equal to 36,000 pounds and or 36 kips. Okay, so I guess that's all that we have for the Red Shear stress. And in the next topic, we'll move on to torsional shear stress as a strains.